Next up, we have Yuwei presenting the CaQR work, which is basically a compiler-assisted approach to reusing qubits through this new feature available in some quantum hardware called dynamic circuits. Yuwei is a PhD student at Rutgers University. Yeah, and he will tell us all about the work that they did for this in building this compilation approach. So just let him get it set up here.
Hi, everyone. This is Yuwei. I'm a PhD student from Rutgers University. And I will present our work, CaQR, a compiler-assisted approach for qubit reuse through dynamic circuit. And this work is done in collaboration with colleagues from IBM and Rutgers. So today, quantum computing has potential to solve many problems that are impossible for classical computers to solve. It could lead breakthroughs in many fields like security, chemistry, drug discovery, machine learning, and optimization problems. However, we are still facing many technical and theoretical challenges. We need to overcome those challenges to reach the full potential of quantum computing. One of the challenges is the limited number of qubits. Starting from 2019, IBM built their quantum processor named Falcon with up to 27 qubits. Until now, the largest machine they have built is Osprey with 433 qubits. And they're expected to build a machine with more than 4,000 qubits. However, this is still not enough to reach the full quantum error correction. Another challenge is limited qubit connectivity. For example, here are 3 machines from IBM, Google, and Eddy. And for those machines, any 2 qubit gate has to be executed on 2 connected physical qubits. So in order to run a quantum circuit in those machines, we have to insert a large number of swap gates, leading to significant execution time overhead. Another challenge is the low fidelity. Quantum qubits are sensitive to environment disturbances and noises. They are subject to decoherence, relaxation, and readout errors, etc., and also error variability. So for example, here's the part of IBM Mumbai machine with qubit error variability. So in order to solve those problems, we propose our work, a compilation framework, CaQR. It uses mid-circuit measurement and qubit reuse to mitigate the qubit shortage challenge. And qubit reuse also alleviates the connectivity burden with fewer swap gates. And it also improves the fidelity by up to 20% in real machines. So what is qubit reuse? Qubit reuse is the process of measuring a qubit that has done all its operations and resetting it and using it for a new logical qubit. Here is, for example, this is Bernstein-Vazirani BV circuit with 5 qubits. So for this circuit, we can reuse Q1. So for this circuit, we can see Q1 finish all its operations earlier than other qubits. So we can reuse Q1 for other qubits. In this case, we can reuse Q1 for Q2, and for the same circuit, we can only use 4 qubits to finish all the operations. We can further reuse Q1 for other qubits. So eventually, for one n qubit BV circuit, it can use as few as 2 qubits. So here comes the question: do current quantum circuits really need so many qubits? We think the answer is no. We found out that there are a lot of qubit reuse opportunities. For instance, we show the result of 2 64-qubit QAOA circuits. And in the first circuit, we show the one with power graph or power law graph. And in the second circuit, we show the result with random graph as the input problem graph. In these 2 figures, the y-axis is the circuit depth and the x-axis is the qubit usage. From these 2 figures, we can see that we can reduce the qubit usage without increase the circuit depth significantly. For example, for this power law graph, even with 80% qubit reduction, the circuit depth still remain low. And for this random graph, we can have 50% qubit reduction and without increase the circuit depth dramatically. So we can dramatically reduce qubit usage without significantly impacting the circuit performance. By far, we have talked about the benefit that leveraging qubit reuse could reduce the qubit usage. It also has other benefits. We can use qubit reuse to reduce the number of swap gates. And for example, for this BV5 circuit, if we want to run it in this hardware coupling with this qubit initial mapping, then the gate in red is not executable since it is mapped to physical qubit that are not connected to each other. So we need to insert swap gate to make Q2 connect to Q5. But with qubit reuse, we can reuse Q1 after Q1 finish all the operations for Q2. And then Q2 is connected to Q5 and the gate is executable. Another benefit of leveraging qubit reuse is we can find better qubit mapping for new logical qubit and improve the circuit fidelity. Here for example, here we map logical Q2 to physical Q23, which is the one with highest readout error. With qubit reuse, we can map Q2 to where Q1 mapped to after Q1 finished. And then we avoid the physical qubit with high error rate and improve the circuit fidelity. So in order to better reuse qubit, we define two qubit reuse conditions, and then we also introduced two methods, QSCAR and SRCAR. We design our compilation framework with the considerations of target applications and use scenarios. For the target application, we consider general applications like QFT circuit and BV circuit. And then we also consider applications with commuting gates like QAOA circuits. For the use scenario, we propose a method QSCAR focuses on qubit saving and SRCAR focuses on swap reduction. So let's first talk about this qubit reuse condition. If we want to reuse the physical qubit of Qi for Qj after Qi finishes, then Qi and Qj cannot be in the same gate. And for the second condition, we need to construct diagraph first based on the gate dependency in the original circuit. And then from the diagraph, any of Qi's gate cannot depend on any Qj's gates directly or indirectly. So here's an example. Can we reuse Q1 for Q4? And the answer is no, because the condition 2 is violated. So from this real dependency, we can see that Q1's gate it indirectly depends on Q4's gate. Based on the two reuse conditions, we propose our methods. QSCAR focuses on the qubit saving, and it evaluates and ranks each possible qubit reuse pair, reduce one qubit at a time until certain criteria met. Specifically, we use coloring and perfect matching for above steps. And in this method, the qubit mapping process is decoupled from the reuse process. Another method is QSCAR. It focuses on qubit swap reduction. It does qubit mapping on fly with qubit reclaiming. And reclaiming qubits enables better new logical qubit mapping. And in this method, a logical qubit is not mapped until it runs its first gate. And we also delay non-critical gates, give rise to more mapping choices for new logical qubit that involving the critical paths. For evaluation, we use four metrics: qubit usage, two qubit gate count, circuit duration, and total variant distance. For those metrics, lower are better. For the benchmarks, we use regular benchmarks, and we use benchmarks with commuting gates like QAOA circuits. We use IBM Qiskey at baseline with highest optimization level 3. And for the QAOA circuits, it contains the classical part, so we use Qubit classical optimizer for it. First, we compare QSCAR with baseline. We have two versions of QSCAR. The first version is maximum reuse version. And in this version, we try to reuse qubit as much as possible. Another version is minimum depth version. In this version, we compile circuit with different number of qubit reuse and find the minimum depth among the compiled circuits. So first, we compare qubit usage. So we can see here our maximum reuse version has the lowest number of qubit usage. And then we compare the circuit depths, and our minimum depth version has a smaller circuit depth than other two methods. So there are trade-off between the qubit usage and the circuit depths. For example, in this QAOA circuit, in our maximum reuse version, it has the lowest qubit usage but highest circuit depths. We also compare QSCAR means-of version with SRCAR. For example, for the QAOA circuits, our SRCAR version has even smaller number of swap gates than QSCAR means-of version. we did TVD comparison over 3 regular benchmarks, and our SR car method has smaller TVD than the baseline. We also did real machine experiments with QAOA circuit to solve max car problem. In these two figures, the x-axis is QAOA runs and the y-axis is the expectation value. It reflects the total weight of cut edges. So lower expectation value is better. And our method shows the lower expectation value than the baseline. To conclude, we construct CaQR, a tool to identify qubit reuse opportunities. And our tool can target different applications and different use scenarios. And our evaluation showed that we can reduce qubit usage by up to 80% while keeping the circuit duration shorter, reasonably short, and also improve the circuit fidelity up to 20%. And thank you. I'm happy to take questions.